One of the things that I found quite hard to get into and hard to understand was some of the broader patterns you see in functional programming. So what I mean is, you've decided, yeah, I'm going to do some functional programming. You sit down at your keyboard and go, right, what do I do now? What's the kind of patterns I apply? Whilst also getting my job done. So what I thought it'd be fun to do today is to look at just two kind of broad patterns. And rather than talk abstractly about how they work and their benefits, I thought it'd be better to look at just ordinary code you kind of do when you're building apps, sort of kind of dull code, I guess, really. But look at what it means to apply some of these functional patterns to that sort of development. So that's what we're going to do is go through the day in the life of a functional programmer. We're going to put on some functional goggles and look at sort of fairly dull problems and see what they look like when we apply some of these functional principles. So the agenda is really simple. We're going to look at 3 code examples. And I apologize to the people right at the back. There's going to be quite a bit of code, so you might need to come forward unless you've got great eyes. So 3 examples. The first one, we're going to look at some really simple data structure stuff. I'm hoping that will be fairly straightforward. And then we're going to look at another example where we're going to build up one of the patterns from first principles. And I'll explain why we're going that route when we get to that section. And then finally, we're going to sort of breeze through another example, just looking at where these patterns reoccur again and again. So that's the plan for this evening. As I go through this, there's kind of 2 things I'm hoping you'll look out for. The first is that functional program is for everyone, I think. And what I mean is, you're going to see some techniques that maybe are new to you, and some of them have odd names, but they become natural with practice, just like all the other techniques we've learned, in our careers as programming. They just might be slightly different. And also, I think these techniques, although they're interesting and exciting, they're just useful, right? They let you get your job done. And in particular, I think they make making change easier. And I think that's because they make your code easier to reason about, and I think it's because they make your code a little bit more modular. I'll try and call out examples of that as I go along. So that's the plan. So let's get into this. And we start a day as our functional day in the life of a functional programmer with what you would normally do, maybe a morning stand-up to talk about the problem you're working on, what you're going to do next. And yeah, it's a slightly contrived example, I agree, but essentially we're building some kind of web service. We're some sort of customer relationship management tool. There's a database with some data in it. Kind of doesn't really matter what. There's a REST service on the front. It's pretty straightforward stuff. So what we've got so far is we've got a very simple web endpoint, which is we can make a request for all our customers, let's say. Which will appear here any second, I'm sure. Or maybe not any second. We may have a slight problem. It looks great here. It's really good. Maybe the backup plan, okay. Okay. You kind of don't even need, you can totally imagine what this does, right? You make a web request, and what you're going to get back is a hunk of JSON. We've all done this, you've all seen this, I'm guessing. You get back like an ID, maybe you get the name of a person, you get their phone number as an array of JSON. It's really kind of, that's as far as we've got in our application so far. But I really would like to show you the next slide after this one. Reboot the thing, whatever the thing is. Yeah. Oh, that's done something. Yep. We did. It worked. This is not even my laptop, so it should really work. Okay, so we're going to pick up some new work. This is like normal behavior, right? This is what we've done so far. We're going to do some new work. Nothing special here. So I'm going to pick up this new ticket, which is, okay, we're saying these customers we've got, they're going to have a subscription so we can send them stuff. I've said a magazine here, but whatever. They're going to have a subscription to a thing. So it sounds like we're going to just add a field to a record. And I'm so sorry, there's another little technical hitch here. I'm just going to wiggle mouses around and hopefully things will sync up any second. Yeah, they do. Okay, so we're going to, it's all going to be fine from now on. Nothing else is going to go wrong, I'm absolutely sure. So we're just going to do this little bit of work. We're going to add a field called subscription to a customer record. Has anyone done anything like this before in their job ever? It's pretty basic stuff. So we're going to dig into this ticket, right? We're going to ask, okay, so what do you mean by subscription? What is this about? And we say, oh, well, actually, someone can never have had a subscription. They've got no subscription. Maybe they've got an active subscription, or maybe they've let their subscription lapse, like it's expired, or they've not paid their bill, whatever it is. And a functional programmer will say, oh, this is an algebraic data type, and we're going to use structural recursion. Now, these are the phrases that get used. And they're unfamiliar names, but they're really simple ideas. So let's just run through this very quickly, so it is quite simple. Now, I'm going to write some code. You're going to see some code. It's Scala code. I'm not going to try and teach you Scala. But it's just code. You're going to find this, I'm guessing most of you are Java developers, you're going to find this pretty straightforward to follow, I think. And do feel free to come forward if it's hard to read. So we're going to start off by modeling this subscription. And this is like, it's a trait. It's like an abstract class or an interface. It's just a kind of marker to say, hey, there's such a thing as a subscription. The Scala-specific thing here is we use a word called sealed up there. And that's telling the compiler, you're about to see all the possible kinds of subscription. And we'll see why that's important in a minute. So we can just bang them out on our keyboard, right? Where we can say, what are the cases of subscription? Well, there's, we've never had a subscription, you've got an active subscription, and you've got a lapsed subscription. Actually, that's probably not quite enough. Let's change one of these, because an active subscription maybe could expire. So maybe we'll have a field on active, which is an expiry date of some kind. And that is all I mean by an algebraic data type. It's a representation of some data where you've got choices. So you've got a choice between never, active, and lapsed. And you've also maybe bundled in some other data, like an expiry date. And we can add that to a customer really straightforwardly, right? Here's a representation of a customer. It's got an ID, it's got a name, a phone number, and now it's got a subscription field. So that's wonderful. We're kind of a long way into our task, but it's not very interesting yet, right? What else do we need to do here? Well, we probably need to store this in a database. Probably need to add that subscription to some Json, fine. We'll look at aspects of that later on. What I want to do now is look at how you manage subscriptions, how you manage switching between different kinds of subscriptions. So we might write a method like this called transition. So this is how you write a method in Scala. It takes two parameters, a subscription and a date, and it gives you back a subscription. And those three question marks, that's just a placeholder for what we're going to fill in. So what would the implementation of this look like? Well, we don't have to think about this too hard. We've done the thinking. We've modeled the domain already. And this is a kind of pattern with algebraic data types. Once you've laid out the data, you just have to deal with each case in turn. So let's do that. That's the structural recursion part, by the way. So let's do that. There's a feature here in Scala called pattern matching. So we're saying, hey, that subscription you gave us, what kind of thing is it? In the case that it's lapsed or never, we're going to do one thing. And in the case of an active subscription, we're going to do something else, right? The stuff to the right of the fat arrows. So if it's lapsed or never, we're just going to do nothing, right? We're going to return our subscription. And if it's an active subscription, we want to do a little bit more, right? We want to check to see if it's actually expired, right? So we just fill that in. We'll say if our current date is beyond expiry, if that's the right way around, then, hey, we've lapsed. Otherwise, we leave the subscription unchanged. Is everyone okay with this so far? This might be a little bit different syntax, but I think the idea is meant to be, there's nothing really interesting here, right? It's just a particular pattern. If anyone has any questions about this, ask them now. We're going to add on to this in a second. So the first thing that inevitably crops up with this pattern is, well, in the real world rather, is we get a change request, of course. Oh yeah, there are other kinds of subscriptions as well. You need to go and deal with those. Maybe we have free subscriptions. So that's okay, that's really easy to handle. We go back to our original code, and we just add in another case, right, called freebie. And if we don't change our transition method here, that's going to be a compiler error or warning. We haven't dealt with all the possible cases. This is the first thing about this particular pattern I find incredibly useful, right? You can sort of decouple a description of your domain from how you're going to go and handle it. So you don't have to kind of shoehorn methods into an object hierarchy, which maybe don't really even fit there. You can just go, okay, the function for handling transitions is over here, right? And the compiler is going to watch your back on whether you've dealt with all the cases. So that's like one simple part of this pattern, if you like. It's called, exhaustivity checking. So that's one thing we like. But there's something else this helps us with, and that's this code is a pure function, which is great. We love pure functions, but it doesn't kind of do anything, right? It doesn't send emails, put things in databases, it doesn't do any of that stuff. So this is great for testing, but doesn't do anything. So what if we wanted to, say, send an email or a text message to people who had just become lapsed? What would we do? Well, we could, stuff some curly braces in here and whack in a send email call, right? We could do that. But we're functional programmers, right? We don't want to do that. We don't want to mess with the purity of this function. So what do we do instead? What we're going to do is move those side effects outside of our code. And algebraic data types help with that. So let me show you what I mean by that. So we can change this transition function, right? We can change it from taking a subscription and giving us back a subscription to being something that takes a customer and gives us back an action. I'm not going to fill in the details of this. It's the same thing, right? You know what the deal is with this kind of system. You write out the matching patterns. But what does action look like? Okay. Well, it's going to be another algebraic data type. Okay. We're going to have a sealed trait called action, and then we're going to have instances of action for whatever we want to do. Maybe we want to do nothing. Maybe we want to encourage renewal, which is kind of a bit of a mouthful. Or maybe we want to expire the customer. Whatever actions are relevant to our domain. That transition function is still completely pure, right? It doesn't produce side effects. What it does is produce a description of a side effect. What do we do with that? Well, at the end of the world, we can actually go away and perform that action somehow. So I've written a method here called perform that takes an action, and it produces unit. Unit is sort of Scala's no-value representation. It means basically there's a side effect is going to happen. And the body of perform, we could have written almost blindfold, right? Because we know, oh, it's an action, it's an algebraic data type, so we just, bang away at our keyboard, dealing with each of the cases in turn, which actually kind of sounds terrible. Actually, it's quite a nice way to work. Working without thinking is a good thing, in my opinion. That's the basics of the first pattern, this algebraic data type and structural recursion. I want to show it how it occurs in just typical application level code, right? And if you squint at this, kind of what we've done here is written a mini language for dealing with actions, and we've written an interpreter for executing those actions. And this is a fairly common pattern in functional programming, where you describe the problem and then you do something to manipulate and actually sort of crank the handle on that description to produce an effect. So what? In our day in our life so far, we've written sort of 20 lines of code or something, so that's definitely time to take a coffee break, get some coffee and cake, and think about what we've seen so far. And what we've seen so far is just a modeling technique called algebraic data types. They're pretty safe. The compiler backs you up quite a lot. They're also very versatile. I've shown you in our application, a domain level, but they also appear as fundamental building blocks in languages, so in libraries, sorry. So, for example, in Scala, the representation for a list is an algebraic data type. It's made up of two cases, an empty list, and then a value plus another list. And using that, you can pattern match and sort of deconstruct a list to pick out elements if you want. And you've seen how this starts to separate data from behavior. And it helps us isolate side effects. And I think that's good stuff for making our code kind of readable and maintainable. So that's the kind of first example I wanted to get through. We haven't really finished that ticket, though. There are other things we need to do. And one of the things I'd like us to do is change our representation format so we get a subscription in our JSON, right? I've added an object in there called sub, which has a type in it called expired. It doesn't matter what the format is. It could be whatever your favorite JSON format is. That's not the point of this. Now, if we were sitting down to write our code to actually implement this, kind of the bottom line is we'd use a library, right? This is a solved problem, basically. But those libraries not all, I've not done a survey, a large number of these libraries follow one particular pattern. And what I want to do in this part of the talk is build that pattern up for you, because I found when I came to use these libraries, I get these weird error messages, and that would be due to not understanding the underlying pattern. So the pattern is called type class or type classes, and it's really all about building up big things from little tiny building blocks. And that's a very good thing, right? Because generally speaking, we're quite good at writing small pieces of code. And if you're like me, you're not so good at writing big pieces of code. So let's take a look at this problem. We're going to build up the problem, a solution to turning data into JSON text. Okay? We're going to do it step at a time. So the first basic problem is, what about if you've got a primitive value in your language, like a 7, which is an integer? How do you turn it into a textual representation you can sort of send down the wire to a browser? And in Java and in Scala, you can just call toString on it, right? That will give you, it looks the same on this slide, yeah? But we know as programmers, there's a big difference between an integer and a string. And we can do that with other types, okay? So we can take a string like hello, and to turn that into a JSON representation, I've said here, you just whack quote marks around it. It's a bit more complicated than that, but let's just go with this for the moment. And these two little pieces of code conceptually allow us to build up something bigger, right? They conceptually allow us to correctly encode a string like hello with quote marks around it, and they allow us to correctly encode a number like 7, which doesn't have quote marks around it. And if you're thinking in terms of functions, then what we've got here is really two functions. One that goes from an integer to a string, and one that goes from a string to a string. So to build on this, what we really want is something that goes from some type T, we don't know what it is, to a string. Then I can represent anything in JSON. That's what we want to get to. And that's what type classes allow us to express. So let's sort of crank the handle on this and see how it works out. So the first thing we do is name the type class. So here, I've created an interface or an abstract class called JSON format. And it's parameterized by a type called T. This is entirely abstract. Oh, the square braces, think angle braces. It's just type parameter. So this is generic at the moment. And what it's saying is, to be a JSON format for some type T, you have to implement a method called format. That's the deal here, if you like. And what does format do? It takes the value of the type, whatever it is, and gives us back a string, right? That's what we want to do. And we can implement instances of this pretty easily, right? Here's the two from earlier, right? We can have an int format, which, what's it mean to be an int format? Well, you're going to implement a format method that takes an integer and gives me back a string. And likewise, for a string formatter, I'm going to take a string and give me back a string with my hokey string quotation mark rubbish there. So that gets us not very far, really. Now we can call two functions in exchange for like 2 lines of code. That's not very useful. So how do we make this very general? So the way we're going to do that is we're going to write a function called output JSON. Our output JSON is going to be amazing. Output JSON takes any type at all and a value of that type. And if you give it a JSON formatter, it will format it for you. You should be thinking this is kind of pointless at this point. Right? You should be thinking, yeah, obviously, right? You've given me a value and a formatter for that value. Sure, I can format the value, right? I call the formatter with a value, right? It's pretty straightforward. Oh, Scala, by the way, has multiple parameter blocks. So that's just a kind of a language feature here. So you can see the way we call it here, we call it output JSON 7 and another set of brackets int format. And you're about to see why that's useful. How terrible is this so far for understanding? Are we following along? This is not too weird so far. We're just defining methods and type values and calling them. Okay, so the powerful bit now starts to kick in. So what I'm going to do now is change 4 lines of this, and I'll talk you through what those 4 lines are and what it means. Okay. So we changed, the first thing to notice that we've changed is the definition of output JSONs. That's a 3rd yellow line here. And what I've done is I've added a keyword to that second parameter called implicit. Now, implicit is a feature of the Scala compiler. What it's saying is, hey compiler, if I don't provide this parameter for you, you can go and fill it in for me. It's given the compiler permission to do that, is the way I'm kind of explaining it here. We can absolutely still provide it if we want, but the compiler, if we don't, the compiler can go find it by a mechanism called implicit resolution, implicit search. So you notice the last line here, I've just say output JSON 7. So what does that mean when this code is compiled? Because this is all happening at compile time, by the way. What it means is the compiler goes, oh, output JSON 7, fine. Oh, this takes 2 parameters normally. But the second one's implicit, so I can go and search for it. What is a reasonable value to put in here? What could the compiler possibly find? Those values come about because of the other 2 changes I've made. It can't just use any old value, right? That would be chaos. It has to use values we've marked as being kind of okay to use. So I've said here implicit value integer format. And that's saying, hey compiler, if you need something of this type, here's an instance, go grab it. So when we compile this code, the compiler goes, oh, I need an extra parameter here. What type of parameter do I need? Oh, it's a JSON format of T. What's T? Oh, it's an integer. Is there a JSON format of type integer I can drop in here? And the answer is, yeah, we defined it up there. Okay. So this will compile and run and output 7. I could put in here a string, and that would run as well, yeah, because we've defined a formatter for string. I couldn't put a date in here, right? Because the compiler will go, I need a JSON format for a date. There's not one defined. I can't just conjure one up. This is a compile time error. So this is the starting to get a bit more interesting, I think, now. A bit more, this is the compiler doing some work for us. Let's just take this a step further to see where we get the real benefits. So let's say we want to output an array of strings, or an array of integers, or an array of integers. Right? How can we do that? We don't want to write a formatter for an array of integers, and then an array of string, and another one for an array. We just want to have the building blocks and have them combined. So how would we go about doing that? Well, we just follow the same pattern we've already seen, right? What does it mean to be able to format a list? Well, we have to go and write a JSON format for a list of something, okay? What does that mean? Oh, we've got to write a format method. It's going to take a list of something, it's give it back a string. This is the same process we've done for integers and string, but now we're doing it for a collection. So what would the body of this look like? Well, we know arrays have these square brackets at the beginning and at the end, and in the middle they have some formatted values separated by commas. So we can fit in the last line of this pretty easily. Where do those formatted values come from? Let's see if we can fill that in as well. We've been given some values, right, as parameter to format, so we can go for every value that we have for v in values, we're going to yield or emit something into a new list. What should that be? What should we be putting into these formatted values? Well, that kind of depends on what's in the list, right? So we can do the same trick we kind of use for output JSON here. I'm going to change 2 lines. So we can say, to be able to call this method, the compiler has to go and find a JSON formatter for whatever's in the list. Okay? Or I can provide one, right? That's fine too. But implicitly, the compiler can go and find it for us. And if it can find it, this will compile. And then what we can do here in the second line I've highlighted is go and use that to format our values. And that completes the implementation of this method. Right? We can now go, output JSON doesn't change at all. We can now say, output JSON for list 1, 2, 3, 4, and we'll get what we expect, right? So think about how that works. The compiler goes, output JSON, okay, I can do this. I've been given a value of list of integers. Is there a formatter for it? Well, there's this method here. If I could call that method, I'll get one. Can I call this method? Oh, well, I need to go and find a JSON format for integers. Can I find one of those? Yeah, I can. We defined it on the last slide, right? So this is a very powerful mechanism for recursively going off and searching for values that the compiler can use to complete your program for you. This is something I'm guessing is not very familiar to Java developers generally. I don't know, but I don't think it's too bad in terms of concepts, right? And it is very powerful, right? So it may not be obvious from this, but we automatically get the ability to do lists of lists. And if you crank the handle on what the compiler has to do, what's the value here? It's a list, okay. Do I have a way to create a formatter for list? Yeah, I do. I have this list format method. What's in my list? Oh, it's another list. Do I have a way to format that? Yeah, I can call the same method again recursively. And finally, that list has integers in it, and we know how to do that. And this recursion all unpacks and gives us a value which can format lists of lists. And if we wrote a formatter for objects, we could then represent lists of objects with containing objects that contain lists, all from independent building blocks, like 4 building blocks that the compiler will combine for us. I think that's really a very powerful pattern, and you see that pattern a lot. So let me just describe the pattern to you. It's called type class pattern, or type classes rather. And these names, by the way, algebraic data type classes, I didn't in Scala import anything called type class, or these are very generic ideas. They exist before Scala. You'll find them in lots of programming languages. They've been sort of proven to be patterns that are useful. I just happen to be showing you the Scala way of representing them, right? But the key idea is you have these small building blocks that are combined by the compiler, and this pattern is used absolutely everywhere. So I'm not going to talk much about the database, but let's just give you a really kind of feel for how this pattern appears again and again. So if we look at this line of code here, this is from a database library called Doobie, which is able to represent queries for you. What this query is saying is, run this select, and I want back a customer object. Think about what it needs to do. It needs to go to our database and look at a name. That's probably a varchar. And it needs to look up the ID. That's probably a long, okay? And it needs to be able to convert them into our language, right? Into strings and longs or whatever we use here. And you think to do that, the library comes pre-built with a type class for that, with standard instances for strings and numbers and all sorts of things you commonly use, but not for stuff we've invented, right? Why would it? There's no way it could know that I want to represent a subscription. How do I represent a subscription in the database? Well, the details of this don't particularly matter, but this particular library lets me describe how to map a subscription to a string, which is my chosen representation here. And basically I'm saying, just use a character for each of the different classes, and it'll do bidirectional mapping for us. But it's the same pattern, right? And if you didn't know this, when you ran the code, you get a compile error, something like, it'll be something like, could not find implicit value for a meta of subscription. And you'd be like, what the hell does that mean? Oh, what it means is I haven't provided an instance of this type class, right? So understanding how this pattern builds up is super helpful to be able to use all these libraries. And generally speaking, you don't write a lot of type classes. Well, I don't find I do, but I use an absolute shed load of them. So we've seen these two patterns, these ADTs and type classes. That's probably a really good chunk of our day in the life gone already. I think in the time left, what I'll do is run through just another example where we kind of see these patterns again, just to try and help bed in the idea of how frequently these things are used. So here's another possible story, which is, I want to be able to update my name, I want to be able to update my phone number, that kind of thing. So I want some sort of web service to be able to do this. I'm probably going to accept a patch request and update fields accordingly. So the details of the web service we've got currently is not especially relevant today. We've got some kind of API that depends on a database. This is a library called HTTP4S, by the way. And we've got a couple of endpoints, right, which is using pattern matching or structural recursion again, which we've already seen, although in slightly different ways. And we're saying, if you hit /customers, I'm going to give you a list of customers back. If you ask for /customer123, I'm going to go to the database and find it. And what will happen if I go to the database and try and find it? Well, there might be one there, or there might not be one there. Right. And this is using another algebraic data type. The option type in Scala is an algebraic data type, and it has two instances. There's none, or there's some value. So, in our Scala code, we can just match those two examples out. If we found a customer, great, 200. If we didn't, that's 404. Go away. So what do we need to do to sort of deal with a patch request? Well, it's kind of like this. We're going to take some JSON, decode it, look up a customer. If we find a record, somehow apply the change to the record, stuff in the database. Okay, straightforward stuff. So what do I mean by a patch? I mean something simple like this. Maybe we'll get some JSON with a name in it. Maybe we'll get some JSON with a name and a phone number in it. Maybe we'll just get a phone number. I don't know. So how do we think about that as a functional programmer? We think about it as, well, we've got a function here that's taking a customer and a patch, and it's giving us back another customer. Obviously modified by what's in the patch. So how would we represent that? Well, maybe our customer record is kind of unchanged here. But our patch would be, well, we don't want them to update our ID, right? We don't want them messing with the primary key. But how would we represent name and phone number? Well, they're both optional. We might get them, we might not. So we represent the patch as an optional string, and the phone number is an optional string. What we want to do is just imagine we can solve this problem. And let's imagine there is a type class for doing this called merge. And we're going to merge between two things. We're going to merge into something from something else. So into a customer from a patch. So we go and sort of define the contract for this. To be able to merge something means I implement a merge method that takes one thing, a thing to update, I get back kind of the original value. So now the question is, okay, so how do we use that? This should be starting to look familiar, right? Because we're going to use the same pointless-looking trick we used earlier, which is to say, well, merging's really easy, right? If you give me a way to merge something, I can call it. It's great, right? Now the trick is, of course, well, how do we start to bootstrap the merging process, right? How do we write this? How do you write a customer merge? That is a merge between customer and a customer patch. Because you can write that by hand, right? You can totally write that by hand. You can say, okay, I've got a customer, I'm going to look at the name field, I'm going to look at the patch, I'm going to look at the name field, do I have a value? Oh, actually, at this point, what I need is a way to merge fields. I need a way to be able to merge a name, which is a string and an optional string. And you could do that for name, for phone number, for whatever else, right? This is, again, should be sounding familiar, right? We want a little building block that we can apply. Now, to fill out customer merge, you could do it by hand, as I said. I'm not going to do that. There's a mechanism in Scala for taking these apart and then asking implicitly for a merger for each field. I'm not going to get into that today. But I'm going to show you one of the building blocks you might use, which is to say, okay, what does it mean to be able to merge a string with an optional string? And what it means is I have to implement this method. The method takes a string and an optional string. And the value is, well, if you gave me a value, it's that. That is the value, right? If you didn't, then it's what we started with. That's one little building block for dealing with optional strings. In fact, that could be generic. It doesn't really do anything with strings. It could be for any value and an optional value. And if we do that, if we somehow generate the customer merge, and there's a mechanism of doing that, as I mentioned, it's kind of deriving instances is the kind of buzzword you'll hear around it. We can call merge with a customer, and let's say we just want to change their name to Robert. That will produce a value for us, and it's producing it at compile time. If this code compiles, it will do this, right? There's no runtime reflection or anything like that. I think that's pretty powerful application of type class pattern. And just for completeness, putting it all together, our kind of ultimate code would be pretty much what I wrote earlier on. We're going to decode a patch. We're going to look up the customer, and then we're going to call this merge. I'm using a library here to build the merge, but that's almost just detail. And I would argue that that code is actually pretty readable. Okay, the formatting's gone a bit wrong on this screen, but I think that's pretty readable and quite easy to maintain as well. But, be interested in your views on that. That got the job done. I think that's probably a good time to end the day in our life. I think we've done a lot of work there, and we've done it using these two patterns. And these two patterns apply across many programming languages. Algebraic data types, very safe, very versatile. We can use it to define languages, write interpreters for them. And you can take that a very long way and create very rich languages that compose and then write interpreters for them, and people do. And type classes, which I think I'm trying to get across, is a very powerful way of programming once you understand what the hell it's doing. And we've done this with Scala, right? And Scala happens to have a very modern, powerful compiler. But I was thinking about this for Brighton Java, and I'm thinking, well, at the end of the day, we're still producing bytecode, right? So in Java right now, you can't kind of do these things very easily, but it's just bytecode, right? So there might be a mechanism. I don't suggest you go implement your own Scala compiler, but it's, as luck would have it, just a few days ago across my Twitter feed, I saw this project. I know nothing about it. This is not a recommendation, okay? Called Derive4J. And I don't know if it's any good or not, but it's got all the right words in it, right? So Java 8 annotation processor, whatever that is, for deriving algebraic data types. Oh, we've heard about them. They're useful. Pattern matching, and in the near future, type classes. So it's really, I think, encouraging that people are working on this. Well, at least 7 people are involved in working on this, and that's with 254 starts. That's not bad. Come on, that's pretty good. And it's being reasonably active 20 days ago. So if this stuff is of interest to you, if you want to explore it, switch to Scala. But if you can't do that, maybe get involved in this. And if someone wants to talk on this and how it works, that would be amazing. I'd totally turn up for that. Okay, I'll shut up now. We've gone on way too long. I think functional programming, I think these concepts are really powerful. I don't think they're weird or hard. I think they are for everyone. And I've tried to explain, I don't know how well that, I think the little building blocks help make change easier. And I'm way over time, so I will stop there. Thanks very much. Mm.